So we're starting out with exponential and logarithmic functions. And what we're looking at first is really exponential decay and exponential growth. Now, exponential and logarithmic functions are actually something that was really a huge advancement, especially in mathematics, especially talking about logarithmic functions. And the reason that they became very helpful is that we can use logarithmic functions to do very big calculations, doing multiplications of numbers like in this here. Because when we talk about, especially with astrology, talking about the stars and distances to other planets, the numbers that we deal with are huge. So, yes. So when they're trying to do these calculations, especially in the 17th, 18th century where calculators weren't a thing, they had to try to use tips and tricks and try to do other methods to try to get at what these are. And they really wanted to go about them, instead of having to do something like this times numbers like this here, which are huge, if we can rewrite it and do it as addition or subtraction, it makes it easier. And that's what they ended up getting at with logarithms, is we can take these logarithmic functions, these big multiplication problems, turn them into logarithmic functions, which require just addition or subtraction, and then reference back. But today, we're not going to get too deep into exponential or logarithmic functions. Come on. We're going to look at exponential growth and exponential decay. Now this here is an exponential growth function, the parent function of an exponential growth. The function f of x equals b of x, where b is greater than 1, is the parent function for the family of exponential growth function with the base b. This graph shows the general shape of the exponential function. Now this exponential function, the reason we know it is exponential is because b, that base, is greater than 1. And what's going to happen is as the value of x, as we increase values of x, it's going to increase faster and faster as it goes along. So might as well, let's pull the calculator out. I'll pull it out here. You guys don't have to pull one out. We'll look at 2 to the x. This here is an exponential growth because the base, 2, is greater than 1. Second table. Well, 2 to the 0 is going to be 1. Anything to the 0 power is always 1. Well, we put 2 to the first. Well, now we're at 2. 4, 8, 16, 32, 64, 20. This thing is increasing faster and faster as the exponents increase. This is even more so if we said 7 to the x. 1, 7, 49, 343. Well, heck, I haven't even gotten 7 to the 4th, and I'm already in 4-digit numbers. So these functions here increase as what we call an exponential rate. When we talk about something that increases faster and faster, we talk as it being an exponential growth. They increase faster. But one of the things about this is that this function here, just the normal exponential growth, will not equal 0. This function will never equal 0. Because as we plug negatives in for x, or kind of talking about b to the negative x, for those negative values of x, well, if x is negative, it moves to the denominator. Because if the variable or the exponent is negative, it goes to the bottom of the fraction. Because that's the way we can make it positive. But can we ever divide by 0? Well, no, we can't divide by 0. And this value of b to the x, as we saw, as it was increasing positively, was increasing faster and faster. And more kind of mathematically speaking, if we took the limit of it as it increased indefinitely, it would get infinitely big. Which means this here is going to get infinitely big. Eventually it will get huge, but it'll never reach 0. It will approach 0, but it'll never get there because the only way that a fraction can be 0 is if the numerator is 0, because we can't divide by 0. And it'll get close to it. So this here, the normal, just y equals b to the x, will not equal 0. Does that mean all exponential growths will not equal 0? Well, no. Because if we can add and subtract numbers, we can move the function up, down. So we can change it so that it can. It just changes the horizontal asymptote, what value it can't be. Now, the other type of exponential that we have is called exponential decay. And as you can see from this graph here, instead of it increasing from left to right going up, it is decreasing. And the main part about this here is that b is between 0 and 1. B is between 0 and 1. Now, we can have it be, there are cases where it's negative, but they're dealing with essentially a reflection across the x-axis of these two parent functions. So here, exponential growth, we can define it when b is greater than 1, and it's exponential decay when b is between 0 and 1. So it's a fraction or a decimal. Now, exponential growth can be fractions because we could have 7/2. It's still greater than 1. Now, one of the biggest cases or kind of real-life situation where we talk about exponential decay is something called half-life. Does anybody know where the term or kind of what area of study half-life comes up in? It is science, it's chemistry. But do you all know what we're talking about when we talk about half-life, or what we're dealing with? Radioactive elements have a half-life. Because when we talk about half-life with radioactive elements, we're talking about how long the elements will actually be radioactive and emitting that radiation. And the half-life tells us and kind of shows us how it's going to decompose and break down into other elements or other more and less harmful, pretty much, subproducts. But will it ever not be radioactive? Well, no. Because for it to be radioactive, it means it has to reach 0. As we just talked about with exponential growth, well, the basic exponential k function will not normally reach 0. It might reach a stable situation eventually, but there'll still be a little bit. It won't be harmful, but it will be minute. And for most radioactive elements, by the time it gets close enough or kind of, I believe it could eventually stop, we would be long since gone. Because we're talking, I think it's tens to hundreds of millions of years for it to actually fully break down. I can show that chart. I normally show it here. I found one that shows the breakdown of radon all the way through. So I can show that here later, because we'll have some time. So, tell it whether each function represents exponential growth or exponential decay, and then graph it. Well, this part of the homework, you're just going to have to identify the graph of it. And you can do that by either graphing it, plugging it into the graphing calculator, or we'll have a trick here that I'll show you here in a minute. So when we look at A, y equals 2 to the x. We consider this to be exponential growth or exponential decay. What do we think? It is growth. Because when we look at the function y equals b to the x, the term that is to the x, if it is greater than 1, it's growth. And if it's between 0 and 1, it is decay. So A, this would be growth. Now, if you're graphing this or looking at graphs and trying to determine which of the following graphs represents the exponential growth or exponential decay, the two numbers that I would kind of look at is 0 and 1. And I would just plug them in. Y equals 2 to the 0. Well, anything to the 0 power is 1. And 2 to the 1 is? So that kind of gives me 2 points. Now, if I'm actually physically graphing this, I'll need more than this, because I'll need at least 3 or 4 points to kind of get the overall shape of how fast it is increasing. But since we're looking at graphs and on big ideas, it's given us the graph already, and we need to pick out which one it is. These 2 points are always going to be good. Because as long as there's nothing being added or subtracted or multiplied, we don't have 3 times 2 to the x, anything to the 0 power is going to be 1. Because 2 to the 0 is 1. 1/2 to the 0 is 1. Because if we start adding stuff, it might change it, but if we're wanting to evaluate it for any number, we just have to plug it in for x. And this would kind of give us an idea for the graph, because I can look and see which one of the 4 graphs has it at 0, 1 and 1, 2. And if we wanted to evaluate it for really any other number, like -3, I can do y equals 2 to the -3rd, which would tell me it's 1/8. Because it's negative, I would move it to the denominator. And 2 to the 3rd is 8, so we get 1/8. It kind of makes sense, especially for the evaluating. If it asks for you to evaluate, you're just plugging in whatever number it is for x and simplifying. Yes. Let's look at the next one. Y equals 1/2 to the x. Will this represent exponential growth or exponential decay? Because? Our value of b is less than 1 but greater than 0. So this here would be decay. And again, if we were looking at it, we could do 0 and 1. But 1/2 to the 0 is still going to be 1. Because I just have 1/2 to the 0. I don't have anything added to it. It's not 1/2 to the x plus 2. I don't have that. There's nothing added or subtracted, so it should be 1 if I plug in 0. And if we plug 1 in for x, we should get 1/2 or 0.5. Because we'd have, and I can write them both out here, 1/2 to the 0, give us 1. 1/2 to the first power is going to be, well, 1/2. Any questions on any of this here? Let's look at the next one. Tell whether each function represents exponential growth or decay, and then graph it. And kind of we've been more or less graphing. I'll actually graph this one here. What do we think? Growth or decay? Even though it has a decimal? It's still greater than 1. Because the value of b, 1.3, is greater than 1, it's still going to be considered a growth. We can do x, y, and 0 and 1 and plug those in. Okay. 1.3 2v x. Graph. And when I graph this here, okay, it is a growth. It has that upward increase that's increasing faster and faster. Second, table. So we see at 0 it is 1 still, and at 1 it's 1.3. Any other questions on this here? Well, let's plug in another number here. Let's say, find out the value when x is -4. So we do 1.3 to the -4. Now for this here, we could do it and this one here is not that bad. We can do 1.3 in parentheses to the -4, hit enter, and it will tell me what the answer is. Now I already have it plugged into the calculator, yes? Because I typed it in earlier. .3501. Because when x is -4, the value of y for this function is 0.3501. I have it here. And there might be more to it. There might be more spots, but that's at least the first 4. Any questions on this? Yeah. Which part? This? Okay. Luckily, we've got time on. I'm guessing 2-finger gesture got turned off. So let's look at this one here. So the first thing it's asking for us to determine is if it's exponential growth or exponential decay. So which one is it going to be for this here? It's going to be decay because the value of b is between 0 and 1. Because all the functions we're looking at are comparing it to y equals b to the x. So if b is greater than 1, it is growth. And if it's less than 1, or between 0 and 1, it is decay. So 1/3. Is 1/3 greater than 1, or between 0 and 1? It's between 0 and 1, so it is decay. If it is greater than 1, it is growth. Now, if I wanted to, I could come over here in the graphing calculator. Alrighty. And go y equals. And so we had I can type in 1/3 to the x. I'm just typing it in to graph it. And that is our decay. It's going down. So I can see it as a decay function. And I can pick out one of the 4 graphs that Big Ideas is going to give me, because it's going to ask me to pick one of the 4 eventually. And I can do it this way. Now, the other thing I can kind of look at is I can go second table and kind of use the table to match it up. Well, 1 1/3 might be hard to see, kind of like with the last one that we did, where we got this decimal. But we also have what? -1/3 is nice, isn't it? So we can use these numbers to match up the graphs. That's it. There might be a few that'll ask you to evaluate the following exponential growth or exponential k for a given number, but it's plugging that number in for x. So any other questions on this here? You kind of feel good with the, it's pretty much, that's going to be about it, especially for the assignment. It's pretty much plugging in one of the 2 numbers, or it's going to give you 2 numbers. You just got to plug it in to evaluate. Determine exponential growth, bless you. Exponential growth, exponential decay. And then the last part of it is determining if the following function is exponential growth or decay, and then picking which of the following 4 graphs it is. So we can type it into the calculator, and it'll essentially tell us what it is. Any questions on these 2? So we can look at both of these here. Now, number 1 would be what? The growth. How about number 2? It'd be decay. The first one would be growth because b is greater than 1. And this is decay because b is between 0 and 1. Even though it is a fraction, it's kind of helpful to see that, okay, maybe fractions will be decay. But we got to make sure that the numerator is not greater than the denominator. Because if it had been 4/3, well, that's the same as 1 1/3, so it's greater than 1. So as long as whatever b is greater than 1, it's growth. If it's between 0 and 1, it is decay. I'm going to turn that back on. Are there any questions over any of these here? Okay. So I'm not going to look at either one of these. I'm going to say this here. It is growth. Because here, b is still greater than 1. Is the negative attached to the 4? Well, it is. It's written in front of it. But what are we taking 4 to the x, yes? Whenever we talk about putting something to an exponent, and I want the number to be negative, what do I have to have around it? Parentheses. Because I've harped on this most of the year, the fact that parentheses -2, close parentheses, squared is different than -2 squared. It'll give you 2 different answers because the exponent square with parentheses is applied to the negative. Without it, it's just applied to the 2. So here, this x is only being applied to the 4. So really what we're looking at is -1 times 4 to the x, so b is still greater than 1. Okay. So now what would it be? Is it's still a growth. It's a growth with a reflection across the x-axis. Because when we talk about decay, and this is kind of where it gets a little tricky, as long as I'm remembering this right, because when we look at this here, hold on. So it doesn't want to graph it because it's not an actual function, so it has issues with it. So technically this wouldn't be growth at all. I'm glad I graphed that because this would be considered a harmonic function. This wouldn't be exponential growth or decay. I'm sorry about that. Got that wrong. Negative 4. The reason they consider this harmonic, and this is completely off topic, is because if we look at this here, we're going 1, negative 416, negative 64, 256. What is it doing? It's going up and down, up and down. It's considered harmonic. It's waves. So it wouldn't be exponential growth. Not right. Now we can expand the model to this here. As you see, y equals a times 1 plus r to the t, and y equals a times 1 minus r to the t for exponential growth and exponential decay, depending on a rate. And these are used for more real-life situations. The value of a car, y in dollars, can be approximated by this here. Y equals 25 times 0.85 to the t, where t is the number of years since the car was new. Tell whether this model represents exponential growth or exponential decay. Bless you. Well, it would be decay because 0.85 is less than 1. It would be a decay function, and we'd really hope, well, we would expect it to be so, because we know that the value of a car does not increase, it decreases after it has been bought and driven off the lot. Tell whether so. Identify the annual percent increase or decrease, because it would be decrease in the value of a car. Well, it would be 15%, because we're coming from the fact that y is equal to a times 1 minus r to the t. Well, our 1 minus r is equal to 0.85. If we subtract 1 from both sides, we get that negative r is equal to negative 0.15, or that our rate is 0.15. I'm not including this on the homework. T, time, the amount of time that has passed. And we can kind of use this overall model, this equation, to figure out how long it's going to take the car to be 8,000. How long is it going to take for the car to decrease from $25,000 to $8,000? Times 0.85 to the t. Now, if this was an ACT question, what we could do is one of two routes. Well, okay, since I know that this is going to be in thousands of dollars, that's 25,000 to start with, I can set it up as 8 is equal to 25 times 0.85 to the t, and go about solving it that way. Or I can grab this and go y equals 25 times 0.85 to the x, because when we graph y on a coordinate plane, we're always in y and x. I'm going to replace t with x. T is our x now is time. We're wanting to know how many years it's going to take for it to go from 25,000 to 8. Yes? For 25 to 8. So it would be 7 years, because that's the first time it hits 8. Yes? It'd be a little bit after 7 years, because we have 8.0144. But unlike my test, ACT gives you what? Option. It gives you multiple choice, yes? Well, hey, if 7's an option, that's the answer. And we can do that with other models, so we can talk about interest rates. How much will you earn per year? Radioactive isotope chromium-51, exponential decay, or half-life. We'll have the same thing here. And I could get into more in depth with this, because if you've taken the PFL class or taking this year should be a familiar equation. PERT, or A equals 1 plus R over N to the NT. The other one is PERT. These here are compound interest. PERT is continuously compound, or essentially the first equation, where the number of times that interest is accumulated is 12. And these here are just different equations that we can have. But I'm really focused on the exponential growth and exponential decay at this point.